Reducing agents, and this particular, I'm sorry, did you start recording?
I just started.
Thank you. This little table right here came out of the Brown LeMay book, but it's very, very nice because it does show the difference between these different, on your standard potential table, okay, it shows graphically a difference between these. So when you're looking at the table, it's a standard reduction table, and if you look at the very top corner of that table, it's got fluorine gas, which is the highest one for the reduction standard. It's also the strongest oxidizing agent, because the oxidizing agent is what gets reduced. And then you go down to the bottom, and these would be the least reducing agents, which in turn makes them the strongest reducing agent. So this is a reduction, but if we flip it, it becomes the reducing agent. Okay. So it kind of gives you a comparison of the different parts of this table, which you already have. Understand what's up here in the top. If you got two different equations, what's on the top is the reduction. What's on the bottom is the oxidation. So just pick two right next to each other, pick two far apart. The one on top will be the standard reduction. The one on the bottom, you flip it, will be the oxidation.
And the most positive one is the cathode.
Is what now?
Is it going to be cathode, right?
The reduction one is going to be the cathode.
Okay.
Red cat.
Red cat.
Reduce cat. Red cat and ox. So you got the two different mnemonic devices. The more positive value for the E naught for reduction is going to be the one on the top. A couple of notes here. It says among the most frequently used oxidizing agents are halogens, oxygens, and oxymorons. No, not oxymorons. Now that I got somebody's attention.
Oh, it's so funny.
I know. Oxyanions. Let me write these down. So these are the most common oxidizing agents. Okay? Most common oxidizing agents. Okay? And they are going to be halogens. They are also oxygens. Okay, oxidizing, that's where the word came from. And oxyanions.
What's that?
An oxyanion is going to be any of those that, the chlorates, the chlorides, the perchlorides, the permanganates, any of those polyatomic ions that have oxygen in them.
Okay.
The sulfates, sulfides, nitrates, nitrites. That would be those.
So like everything we work with ever.
Just about, you know, when you look at this, it's anything with oxygen or anything that halogens are bonded to. So you put these two together, you got an oxyanion.
Okay.
So you take the chlorine and the oxygen, you got chlorate, chloride, that kind of thing. So those are your most common oxidizing agents. And I already said this, the higher on the table, the stronger the oxidizing agent. And that brings us to the next slide. Greater difference between the two, the greater the voltage. We explored this the other day when we took lithium and fluorine gas and looked at those. And if I'm not mistaken, when we did that, lithium and fluorine was 5 or 6 volts. If I remember, we did that in class. Was it 5 or 6 volts, something like that? Real large number of voltage, real large amount. So the greater the distance, the higher this number is going to be. So the true thing that you would want to do to build a good battery is to find two things that are very, very far apart. Yes, ma'am?
Are there not common reducing agents? Or do I miss that?
Do I have common reducing agents?
Or is it not important?
Well, let's take a look at the table there. What would be an example down here of the ones that are down here in the bottom? These are reducing agents. Okay, so we got lithium, cesium, potassium, rubidium, barium, strontium, calcium, sodium, magnesium, beryllium. What would be a trend there?
The alkaline.
The alkaline metals.
First two.
Mm-hmm. Yeah, the alkaline or the alkaline earth metals. So that's a good question. Good question. All right, so we move on to the next one. Now, line notation. What we're trying to do here is learn a system that helps people identify what's happening in an electrochemical reaction. We call it line notation. When you do the line notation, you're going to go left to right, and the left one's always going to be the anode. So in this case, whatever this electrode here is, that's the anode. It's going to be the solid one. Then the next one is going to be the aqueous solution with that same cation in it. So if this is copper sulfate. If this is lead, it's lead nitrate or something like that. Then you have a double line. This separates the phase between the solid and the liquid in the anode side. Then you have a double line, and then we're talking about the cathode side. So we have the aqueous solution in here, and then the solid, which would be the electrode for the cathode side. So anode on the left, cathode on the right. When we draw a line here that separates the phases, and you always start with the solid on the outside, whatever it may be, that defines the electrode. This is going to represent your salt bridge. Salt bridge or the porous disk. And one of the keys that you got to remember on this thing is if all of the stuff in the anode side or all the stuff on the cathode side is a liquid, you can't use liquids for a solid electrode. So what we do is we put an inert substance in there, and most of the time you just put in platinum. Platinum is going to be a fairly inert substance.
Why?
For the electrode.
What does that mean?
How does that affect our line notation?
Well, instead of putting down the metal, solid metal for whatever these aqueous solutions are, you're going to use platinum. So if we're using permanganate as one of our substances, permanganate is not solid.
Okay.
Okay, so we have to use a solid electrode. So what we're going to do is we're going to use platinum as the electrode, and it's inert. It means it's not going to get broken apart and reduced.
Oh, so like down there, instead of saying copper solid, it'd be platinum solid, and then whatever, and then permanganate in the next line.
Right.
Is aqueous.
Mm-hmm.
Okay.
Yeah. Yeah.
That makes sense.
So it depends on what you're using in your redox reaction. So for an example, here's one up here that's oxygen. Oxygen is going to be reduced to oxygen, hydrogen are reduced to water. So oxygen and hydrogen are going to go in there, but you can't have an oxygen electrode.
Right.
Real tough to do. Okay.
So basically, this is just a non-picture form of what we did Friday, right?
Yeah, it's a diagram. They call it line notation. What it is, it's a way of communicating what are the components, in what order are they. It also tells us which way the electrons are going to flow, because electrons are always going to flow from the anode to the cathode. So reading from left to right, electrons are going to flow that way. It tells us what the different parts are, both the liquid and the solid that are in there. So it's a pictorial way of defining a galvanic cell or a voltaic cell.
Charges would be necessary.
Charges would be in there. Mm-hmm. You put charges in there. So the example down here, see I've got copper plus 2 aqueous. So this is in the solution. And then my electrode here, the anode, is copper solid. And then here's my salt bridge. And my cathode, I have iron something, could be iron nitrate, iron sulfate, or whatever, in the solution. And then my cathode is not going to be iron plus 3, because iron plus 3 is an ion. That's not a metal. So it's forming an ion over here. So what I have to do is I have to list my aqueous in order, but I also have to put in a new electrode that these aren't electrodes, so I have to use platinum here for my electrode.
And why do they use platinum?
It's inert. It doesn't start decomposing or it doesn't plate out very well.
Will platinum always be right there on these?
On this particular reaction, yeah.
No, not on this particular
Only
reaction.
when they're all aqueous.
Yeah, if all of the substances in the mixture are aqueous, then you got to have a solid for an electrode.
So, like, if as the reaction takes place, there's no precipitate,
Yeah.
is it back to solubility rules there?
Okay.
Okay. Why don't we list the nitrate?
Because they aren't involved directly in the electron transfer. They aren't being reduced or oxidized. The nitrates and those things are what's basically in the salt bridge to make sure that the circuit is
spectators.
completed. But yeah.
Okay.
So, let's try one here. All right. So, you guys got your reduction potential papers? See if you can dig
Somewhere.
those out. Okay. So, here's my reaction. I'm going to take aluminum with a +3 plus magnesium, and I'm going to produce aluminum plus magnesium with a +2. Aluminum +3 plus magnesium yields aluminum plus magnesium with a +2. So we're going to do a line notation for that particular reaction.
Can you write that on the board?
I can. Go ahead.
Trying to stop it.